Okay? I unmuted it, so we're good now. That's just me setting it up. Can everyone see the product rule there? Right? F prime g plus g prime f. Derivative of the first times the second plus derivative of the second times the first. Now I actually need to take derivatives now. So this should be something you are comfortable with from last class. Because there's a bunch of pluses and minuses, you can do them term by term. So what's our derivative right there? 3x squared plus 2x minus 2. That's it, right? That's derivative of this. Derivative of 1 was 0, so that's that. Then times this. Plus, now I have to take derivative of this. 28x to the 6th plus 1, 0, right? So that's it. And then write the rest of this. And we are going to leave our answer just like this. This is our answer. We're going to box it up. This is what I will refer to as the raw derivative. The raw derivative, meaning that I have not done anything algebraically to clean that up. That is the derivative. All right? That is what it is. Understand? No questions? F prime g plus g prime f. Derivative of the first times the second plus the derivative of the second times the first. So now a little bit of bad news, just a little bit of bad news, little. I'm going to go to your formula sheets, right? You're allowed to have formula sheets for this test, for all tests. Where are your formulas? On your formula sheets, on reference page 5, formula 5, you see that there? Is their formula the same as my formula? No, it's a little different, right? The book, these formulas come from the textbook. The textbook says if you have f times g, don't do the derivative of f. So leave the first one alone, do derivative of the second one, right? Then plus, then leave the second one, do derivative first. Is that the same as what I'm doing? Does it give you the same answer? Yes. Why? Because you're adding, so you can change this, right? And multiplication is also commutative, meaning you can switch the order, right? So basically, if you take mine and move my g prime f in front of the f prime g, like just switch those, that's legal, right? And then to match theirs, I'd have to flip those, commute the multiplication, and over here commute this multiplication. Now that's the book's formula, right? So you might ask yourself, why would I give you this if this is what's in the book, right? I'll explain it in a moment. But I just want to point out that the book has a different formula, all right? Trust me, it'll make sense in a second, all right? But I'm just pointing it out that if you go to that, it's not going to look the same. So I recommend that you scratch that out on your formula sheet. This is one of the rare times I allow you to change the formula sheet or modify it. I am urging you to use this formula instead for the product rule. So scratch it on your formula sheet, put that instead, all right? Do you feel like you need another example of product rule? Do you get the idea? Let's do one more. Let's see if you've got this. Another example, if y equals, how about, I don't know, square root of x tangent x. Find y prime. So is that a product? Is that a product? Yeah, you see it right here. So we can call this the F and this the G. So according to the product rule, I'm not even thinking about that, honestly. I'm thinking about, I'm going to take derivative of the first times the second, plus the derivative of the second one times the first. So I need to take the derivative of the first one. So I'm going to take the square root of x, I need to take its derivative, multiply that times the second one without a derivative, add to that the derivative of the second one, and then times the first one without taking a derivative. Well, let me finish it. What's the derivative of the square root of x? 1 over 2 root x. Remember I put stars next to that, said memorize it, have it ready? You should all be comfortable with the idea that the derivative of that is 1 over 2 root x from last class. And then times tangent x plus, what's the derivative of tangent x? Secant squared x. Good. Secant squared x. This is one of the ones where I said you better have sine and cosine memorized, derivatives, and learn tangent as soon as possible. The other three, just know that you have the formula sheets, but tangent, we use it a lot. So derivative of that is secant squared x times the square root of x. That's the derivative. I mean, that is it. And I could do a little bit of algebra here. I mean, I could take this tangent, pop it on top there if I wanted to. I should probably move the root out in front there just so you don't accidentally think these can go together. Because again, this x is trapped in the secant. So maybe I could have something like tan x over 2 root x plus root x secant squared x. Something like that would be a nice answer. But this on a test would get you full credit, okay? Yes? The book, all right, when you're doing your homework, the notation they might use might look a little different than this, okay? You know how I'm using the prime marks here for my derivative? The book may do this. They might write, okay, I need the derivative of the first one times the second plus the derivative of the second one times the first. Do you see the difference in the notation? Instead of using primes, these prime marks for derivatives, I'm using d dx to say, hey, take the derivative of that. Take the derivative of that, all right? You should be comfortable with both notations. The section 2.6 that's not going to be on this test, we're going to be using this notation exclusively. So we need to be comfortable with it. But in this section, if you want to use primes, you'll be okay. We okay? Product rules seem pretty doable to you? How about this? What if y is equal to x squared over x cubed plus x minus 4?
Split them up.
Can you split those up?
Yeah, you get x squared over you do x squared over 1 times 1 over x cubed plus x minus 4.
1 over 1.
X squared over 1 times 1 over x cubed plus x minus 4.
I'm not sure I'm following you. X squared over 1 times, like this?
No. An entirely new.
Oh, times.
Yeah.
Oh, split it up. Got you, like this. Oh, I got you. Oh, I see what you're doing now. Yeah, you could do that. You could rewrite that way, right? You could rewrite it this way. And you could say, all right, I have a product of two things, right? This you know the derivative of, because this is really just x squared. But this, can you take derivative of this? We haven't learned how to do this yet. And you can't pop these up to the top. You can't because they're separated by addition and subtraction. You can't just make this x to the negative 3, x to the negative 1. What would you do with this? You know what I mean?
You can't literally just do the addition, the sum rule, whatever?
No, because it's in the denominator.
Okay.
We can only do the sum and difference if these were separate terms. Like if we could split this up into something plus something plus something, then we could do them individually. But it's 1 over this entire sum. So we don't know how to do this, okay? We don't. So when you look at this, I want you to now see that this is a quotient, right? Instead of a product, we're going to now talk about quotient. Quotient meaning division. We have division of two things. I wonder if there's a rule for division. Like here we have a rule for products, right? I wonder if there's a rule for division. There is. It's called the quotient rule, right? So I'm going to give you that quotient rule now. These are the only two rules of this section, the product and quotient rule. So here's our quotient rule. I'm not going to prove it. I'm just going to give it to you. So if you ever have a function f of x divided by g of x, that's what we have here, right? We have a top function and we have a bottom function, right? A numerator function and a denominator function. If we've got that, then the derivative with respect to x of this quotient will be, you ready for it? You ready for the derivative of a quotient? Here's the formula. It's the derivative of the f function times the g function. Does that look familiar so far? Is that not the same thing that we did here for the product so far? Minus instead of plus. Now the derivative with respect to x of the g function. And then times the f function. Does that look familiar to you? What does that look like to you? That's the product rule, but one difference. Subtraction, right? So far there's only one difference in these two formulas, right? The subtraction in between them. So far. There's one more thing on this formula. You have to take this entire thing and divide it by the g function without a derivative squared. That is the quotient rule. Now I'm going to say this in words, okay? I'm going to do this in words. This is the derivative of the top, right? That's what this is. That's the derivative of the top. Times the what? This, which is the bottom. You could say numerator and denominator, but I'm going to say top and bottom, right? So you're going to take derivative of the top, multiply it times the bottom, right? Then you're going to say minus, what's this? Derivative of the bottom, right? Times the top. All over what? So over divided by, what's this? Bottom squared. There's other cute little things that can be taught to remember this, but this is the way I remember it, so this is the way I'm going to teach it. All right, so there it is. It looks worse than it actually is. You'll get used to it after a while. Here's another notation. Other notation, a more compact way. Let's say you have f and you're dividing it by g and you want the derivative. Right? So I'm giving you a notation similar to this one. This is what you do when you have a product, you do this, right? When you have a quotient, what you're going to do is the same formula as the product, but with a minus between. And then over the bottom function squared. That's the real nice compact way of writing it. Okay? Let's do this problem real quick. Let's do this one. Does everyone agree we have a quotient here? We have a top function and a bottom function, right? We've got our top. This right here is like our f. This right here is like our g. So the derivative of this, we start by taking the derivative of the top, right? So I'm going to write that. X squared, I need to take its derivative. Times what? Derivative top times the bottom, right? Don't touch the bottom. I mean, don't do a derivative. Just do the bottom here. Now what? Minus, right? The derivative of the bottom. So I'm going to take the bottom, x cubed plus x minus 4. I still need to take its derivative. And then times what? The top, which is just x squared, yes? I'll put it in parentheses. I actually don't need it in parentheses because it's a single term, but I'm going to put it in parentheses anyway. And then all of this over what? The bottom function squared. So I take x cubed plus x minus 4, take the whole thing and square it. I'm not done. I actually need to take some derivatives now, don't I? So if I take derivative of this first one, I get 2x, and then x cubed plus x minus 4, and then minus, I have to take derivative of this now, right? What's derivative of this? 3x squared plus 1. It must be in parentheses because there's two terms, and it's going to multiply times this x squared in the back. Then all of this over the bottom squared. And that is your raw derivative right there. That's your unsimplified derivative. What could we do to clean it up? We could distribute this through, right? And then here, we could distribute the x squared through, and then push the minus through, and then collect like terms, right? That's all algebra we could do. I'm not going to do it right now because we're really just more concerned about applying the formula, all right? Questions? Okay, so let's look at the book's formula for the quotient rule.
Is that different too?
I actually don't remember. Where's my mouse? Oh, there it is. Yeah, thank you. Okay, so for the book, it's not mine either, is it? They look at the top left corner. They do g, do y'all see it? G of x, and then they take derivative of f. So it's my formula but flipped, isn't it? And then on this part, it's this but flipped. So why am I making this harder for you? Am I trying to make this easier for you? So when I was a student, okay, I learned it like the book. Okay, that's the way I learned it. So let's just go look at the product rule. Look at the numerator of the product rule. Or not numerator, look at the, there's no numerator. Look at the product rule. To me as a student, I tried to memorize this formula. And then when I got to the quotient rule, this numerator looks completely different. Doesn't it? They look different. The way I taught it, what's the only difference between the two formulas? A minus here and then the g squared on the bottom. So there's less that you have to remember. You have to remember the product rule, and when you get to quotient rule, just replace this with a minus and then put the bottom squared underneath and you're done. That to me as a student looked like two different formulas I had to memorize because they are so different. They are different if you put them side by side. So with that said, if you go to the tutoring lab and you're trying to get help with product rule or quotient rule, just be forewarned that they're probably going to use those two formulas. That's what they're probably going to do, right? I don't care if you use those, all right? I don't care if you use them, but I personally think that this is just easier to remember because there's such a slight difference between the two formulas, okay? You pick what you want. I encourage this. Right, let's do some more examples. This really allows us to go and take derivatives of lots of things, right? We're kind of opening up the world of functions to ourselves now, because now we should be able to handle any sort of products or quotients. Oops. How about this one? Y is equal to x cubed over secant x. Find y prime. What do you see? A quotient. You see a quotient, right? See a top function and bottom function? When you're thinking quotient rule, start thinking, can you take the derivative of each one of those separately? Can you? Do you know derivative x cubed? Yeah. Do you know derivative secant x? Somewhere, right? We know it somewhere, right? We have that from last class. That you can't, I don't know, natural log of x? Like there's certain things we don't know, right? There's certain things we don't know how to handle right now, yet. So as long as you can handle the derivative of each of these, then you're in business, right? Okay, so to do y prime, I'm going to do, again, I'm not even going to think about the formula, I'm going to think more about the process. I'm going to take the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. So what's the derivative of the top? That's x cubed, oops, take derivative, right? Well, come on. X cubed, take the derivative, that's the derivative of the top, times the bottom, minus, now I need to take derivative of the bottom, and then multiply that times the top without a derivative, and then all of that over the bottom function squared. That's it. We just need to calculate some derivatives. What's derivative x cubed? We said 3x squared times secant x. Okay, minus what's derivative of secant x? So you might have to look it up. We did talk about that last time, right? Secant x tan x. We did talk about that last time, right? It's in, yeah, it's on the formula sheets, but I did mention it, yes?
I don't think so.
I didn't? No? I thought in my notes I did. Let me see, maybe we didn't get to the end of the notes? When we were doing basic differentiation formulas last time, we did derivative of sine and cosine, right? Said, okay, there was derivative of sine. I thought I had said, and then there are others that you need to know, and I just put them up on the board. Maybe I didn't. If I didn't, there they are, okay? There's derivative of tangent is secant squared, derivative of cosecant is negative cosecant cotangent, derivative of secant is secant x tangent x, derivative of cotangent x is negative cosecant squared x. Those are all on your formula sheets on the reference page, yes?
The formula sheet is showing that its secant becomes, you take the derivative of negative secant, and then
What's that?
under hyperbolic functions, d over dx of secant x. Here, right there. It's showing
That's secant hyperbolic. That's a different function. Yeah, we haven't talked about the hyperbolic trig functions. That actually we'll talk about in Cal 2. So that's a different function. Go further up. You're looking at the hyperbolic trig, look at the trig, it's above it. You see them? Yeah, I'll show everyone just so you see it on your formula sheets where these derivatives are. It's on this reference page 5, right here in the middle of the page. It says trigonometric functions, and then it shows the derivative of sine, derivative of cosine, derivative of tangents over there. They're all here, okay? And you get those on the test, all right? You get to use that. You're welcome.
So if it was the derivative of cosine, would you put a plus there for negative?
Good question. If this was a cosine, we would do minus, and then derivative of cosine would be negative sine. So you would have a double negative. It would become a plus. Exactly. Yep. So secant x tangent x, Now what? Am I done up top? Times x cubed. Don't forget the x cubed there. And remember that x cubed can't join these x's, right? All of this over secant x squared. By the way, there's another way we could write that. Secant squared x is another notation we have for that from pre-cal. That notation is equivalent.
You want to pull out a secant x?
You could, if you see that, you could cancel one secant from everything if you wanted to simplify this. But right now I'm just worried about the raw derivative. There it is, right? Questions?
So you're only looking for derivative.
On the test next week, that's the main thing I'm looking for. Now, you should try, when you're doing your homework, you should try and make your answers look like the back of the book. Okay, or not the back of the book, the solution, you know how you can see the solution? You should try and get your answer to look like theirs. That requires algebraic simplification because we are headed there eventually. We are going to be doing that. But just time-wise, I want to just focus on making sure we can do the mechanics of the derivatives first. All right? Everything kind of flowing okay here? How about this? Let's do one more before I start turning the screws. Did I mention the turning the screws in here? Have y'all heard that term before? My other class didn't know what that was either. Y'all never heard turn the screws? Yeah, it comes from torture devices. Back when they used to like put people on a rack and tie up their arms and ankles and stretch them out. Be like, believe in my God. You believe in my God? No? You believe my God yet? You know, that sort of thing.
I wouldn't just assume you're talking about torturing people.
You wouldn't assume that?
No.
No, but I mean, it's not, I didn't make this up. It's called turning the screws. Turning the screws is a term that means you're going to increase the suffering or the pressure, okay? We're going to turn the screws.
You're not liking any of this.
Pardon me?
I said, yeah, I'm not liking any of this.
You don't like this? Okay. Well, it's just the problems are going to get a little harder. That's all I'm trying to say. Okay? The problems are going to get a little harder in a minute. But before I do that, I want to do one more thing. I told my class that the other day, and they were like, you're crazy, you're sadistic. I'm like, man, I didn't make this shit up. I'm not torturing people. Okay. Did y'all see Dahmer? Yeah?
What?
The Dahmer, the Netflix thing? Yeah. Yeah.
No, but I've heard good things.
Okay, let's do this. Yeah, I've seen it. It's crazy. Find equation of tangent line to the curve y equals, let's go with x cosine, let's do x squared cosine x at, where do I want this to be? At pi negative pi squared. This is just going to look weird to you, but yeah. So look, we've been doing this since we first learned about derivatives, right? And I said this is one of the main things we need to be able to do in this class is I give you a function and you go find me the equation of the tangent line to that function at a certain point, right? We've been doing this repeatedly, right? So I'm giving you a curve, I'm giving you a point, and I want you to find the equation of the tangent line to that curve at that point. So what do you need? You need the derivative, right? And you need the derivative at that particular x value of pi. And then once you do that, you're going to use this formula that we've been just beating to death. Day one, I showed you this formula, right? And I said this is like going to be with us till the end of Cal 1. We're going to just use this over and over and over. We have a point, right? We just need the slope. The slope that we're looking for is going to be the derivative of that function at the x value of pi. Whatever that is our slope. So let's get our derivative. We need the derivative first, right? So we have a product. So the derivative of a product is the derivative of the first one times the second one plus the derivative of the second one times the first one. I'm going to write that down. It's the derivative of the first one times the second one plus the derivative of the second one times the first one. Which for us is, let's see, derivative first one there is 2x, right? Times cosine x plus, what's the derivative of cosine? Right, negative sine. I'm going to put in parentheses, negative sine. The reason I put it in parentheses is because notation-wise, it's weird to write plus minus. So I'm going to put plus and then this negative sine x in parentheses. Then next step, I'll change this to a minus. And then out here, x squared. You all buy that? Bless you, bless you. 2x cosine x minus x squared times sine x. So here, again, I put the plus minus, became a minus, and then the x squared, I pulled it out to the front. This is my derivative. This wonderful function here will give me the derivative, it will give me the slope of the tangent line at any value of x I provide it. Now I need to provide it the value of x that I'm looking at, which is pi. Okay? So at x equals pi, right, the derivative is, so I take that and I plug in pi for x. 2 pi times cosine pi minus pi squared times sine pi. You'll see I'm just replacing all my x's with pi's, right? Now in my pre-cal class last week, I gave them a quiz on, they had to draw the unit circle from scratch, right? What's that? Yeah, it sucked, right, back in pre-cal. And I told them in pre-cal, I said, look, I said, I don't like asking students to memorize things because memorization is just, to me, a waste of brain space. But I told them you need to memorize the unit circle. That's one of the things you just need to know. You need to be able to visualize it because when you get to Cal 1, we can't be sitting here fumbling around with our calculators, guessing what the value of cosine of something is. We need to understand it off the unit circle. Now, to be realistic, I realize that a lot of you don't know what these are. So, -1 and 0. Okay? So how are we doing that? How am I doing that? I'll tell you how I'm doing it. I'm looking at the angle pi, which is here, that's pi. I'm looking at, on the unit circle, what this ordered pair is. It's -1, 0. And I know from pre-cal that when you're looking for cosine of an angle, you look at the x-coordinate, and when you're looking for sine of the angle, you're looking for the y-coordinate. So that's how I'm doing it. Cosine of pi is the x-coordinate at pi on that circle, which is -1. So this becomes 2 pi times -1 minus pi squared times, now here, I'm looking at the y-coordinate at pi, which is 0. And so what's my answer? -2 pi. That's a slope, okay? That's a slope. If you're not familiar with this and you'd like to sit down with me in my office for 15 minutes